Yes, well, let me start by thanking the organizers for arranging this workshop on an interesting and very relevant topic, and thanking also them for giving me the opportunity to give this talk. So I'm a physical oceanographer, so I'll be approaching the topic from that side, but in keeping with the spirit of the workshop, I'll try to avoid as much as possible any jargon from the oceanographic side. So, and I'll try to keep things simple. So the main question, of course, or one of the main questions of this workshop is trying to separate geodetic and oceanographic signals. And given the overlapping space and time scales, that becomes an issue. So I'm approaching this from the point of view of modeling the oceanographic signals and trying to do the best we can to do that, to model them so that we can then separate out the geodetic signals. So the outline for my talk then is basically looking at some, I'm not giving you any new results, but we'll try to compile some of the previous results on comparisons of models and bottom pressure recorded data, and see how well we do, and then try to understand some possible factors that might be behind the model data differences that we find, and at the end try to give some discussion of what we might want to do to improve the situation to improve our estimates of oceanographic bottom pressure signals. So so I'll start by showing some results that were basically motivated by GRACE and trying to understand GRACE data, and so they are focusing on large scale and global signals, but it's still relevant for the subject of the workshop, I hope. So and the other thing is there's a lot already being said on some of these things that I'm going to show, so I'll try not to be too repetitive, and hopefully we'll have some fresh ideas from this. So this is a comparison that we did back in 2011, the Queen and myself, on the comparisons of two models essentially. One is a model that was used at the time to de-alias the GRACE data, the OMCT so-called model, and then we used another model that uses data simulation actually to improve the estimates. And all these results that I'm showing here are for periods shorter than 60 days. That's the periods that are aliased in the GRACE data, but it's also timescales that are important for what we're discussing in this workshop. And so at the top right, you have basically the variance of the BPRs in the circles, and the two models in red and blue. And to the left, you have the estimate of the bottom pressure variability from one of the models, and also the triangles represent where the BPR data set is. So you can immediately see from the top that from the top right panel that a lot of the BPRs have very strong variability, which is not represented in the models, in both models. So if you go to the middle panel, that's where I'm showing the variance of various quantities again. So again, the circles are the variance of the BPRs, and then the triangles now are the variances of the differences between the BPRs and the two models. And there is some reduction in variance in many of the BPR sites when you use the model, but there's considerable residual. And what I'm showing at the bottom in green is the difference between the models. So the models agree almost very well in many of the places. But if you look at what they're doing in explaining the BPR variance, there's a lot to be done there. And the bottom panel is the correlation between the BPRs and the models. And of course, in some places like the South Atlantic, some of the BPRs in South Atlantic are not very well correlated at all with the models, and some in the Pacific also. So there's another comparison done more recently with a different model, and this model is also used to de-alias the GRACE data, so-called AOD1B. And this is done now for 3 different frequency bands, 1 to 3 days, 10 to 30 days on the top right, and 3 to 10 days on the bottom left. And so you can see that these are RMS differences between the model and the BPRs. And this is a different set of BPRs, but of course, almost global, but very sparse. And so actually, this is not the RMS difference. This is the percent of variance explained by the by the model of the BPR variability. So if you get 100%, that you explain all the variance. If you're getting less than that, then you have the problem. So what you can see here, that it's very frequency dependent, and it's also very regionally dependent. So you probably get the best variance explained for the 3 to 10 day band. And maybe that's because, this is where a lot of the synoptic forcing is from the atmosphere, on these time scales. And so maybe you're getting a lot of the forced variability from the atmospheric forcing in the models, and you can explain quite a bit of that variability in the BPR. But in other places, you have, as little as 10–20% of the variance explained. So you can keep going like this, and this is just one more recent example, again, of comparisons between BPR and a number of models now. There are a few numbers here, so let me just explain what they are. In the top number on the table is the daily GRACE fields that a German group has been attempting to estimate. And then there are three models. One of is a de-aliasing model, which is a sort of stratified full general circulation model. The other 2 models, DBOT and DAC, are models that use a single layer, so they're supposedly simpler than the stratified models. But if you look at some of the numbers, and again, these are for 2 different bands, the 2 to 4 day and 4 to 12 day periods bands, and you're looking at RMS and variance explained in some of these models of the BPR data set. These are 26 BPR locations now. So again, the signal strength is at the bottom. So you have about 5 centimeters and 11 centimeters on the BPRs. And then what you're seeing at the other numbers are the RMS residuals once you apply the correction from the models. And so one thing that you notice is that if you using the daily GRACE fields to explain the BPR variability, you do better than some of the models, or actually one of the models. So it suggests that the GRACE daily fields have some information that are useful to infer some of these very high frequency signals. The other thing that you can see here is that the models agree. Well, maybe I should say in the parentheses, the numbers in parentheses are the numbers that you get from matching the models to the Grace daily fields instead of the BPRs. And so you can see that the models do better with the Grace daily fields than the BPR, which suggests that there's some missing short scale variability in the models. You know, the Grace fields are smoother and larger scale. So I think enough said about these comparisons, perhaps. And one key takeaway from this is that there's a lot of variance that is left unexplained in the BPR data from using some of these coarse global scale models. And the question then is, what is causing these model data differences? And so what I've done here is I listed, you know, of course you can start from the bottom and say, well, maybe there are some genetic signals that are obviously not represented in the models, and maybe they are contributing to this. The other thing is instrumental data noise, but I think that these are probably small. You know, we're seeing variance of a few centimeters that are unexplained in the BPRs, and some of these signals might be at the lower end, and certainly the instrumental data noise, maybe it's at the level of a few millimeters, but maybe the data people can tell better from that. But I think that the key issue here is model deficiencies, and I've listed a number of them. The list could be much longer than this. But I think you know, some of the key things are resolution, and in terms of resolution, you're also not resolving the domain and the bottom topography very well if you don't have the resolution, and you can also have missing physics, and I'll talk about a couple of things there, and of course subgrid scale parameterizations. These include things like, you know, how the model dissipates energy. You seem to be having a deficiency in variance in these models, so it's probably not an issue of having too low dissipation, maybe too much dissipation, but probably not the key issue either. And then there's also atmospheric forcing, which could be misrepresented in some of what we do in forcing these models. So I'll just have two examples of missing physics or missing missing forcing that I'll try to briefly outline here. So one of the missing physics in most of these models is the effects of self-attraction and loading, and this is of course very important for tides, and tide people usually account for this, but in these coarse global models, we don't really account for this. And so this is an estimate from that we did a couple of years ago, of the possible amplitude of the self-attraction effects for periods of less than 60 days in this case. So this is the RMS values for the potential self-attraction loading effects that we are missing in some of these models, and they range from a few millimeters to up to a centimeter in some of the highest variability in the Arctic. So again, this is good and probably not negligible if you start to want to improve the models, but it's probably not a key issue in some of the missing variance that we see in the model data comparisons. Another thing that tends to be overlooked, and we talked about that yesterday also, is the effects of atmospheric pressure. You know, the effects of atmospheric pressure forcing in the ocean are very important for dynamically in short periods, days, and to up to 1 to 2 weeks. And but this is showing what we get if we say that, okay, well, the inverted barometer is working almost perfectly, but not quite. So what are the values of these deviations from the inverter barometer at periods longer than 60 days. So that's what's shown here. That's sort of the RMS values for that type of signal, and you get something on the order of a few millimeters at places, and down to about less than a millimeter in the tropics. So again, this is not very large, but in some places it might be important to consider, even at timescales as long as 2 months. I think one of the key issues then that I want to focus on for the rest and for the last 3 or 4 slides is the issue of resolution and the issue of missing physics. So if you're not resolving the eddies, so you have a very coarse resolution model like a degree or so, so you're missing all the variability from the nonlinear processes, eddies, instabilities, and so on. And so we've tried to separate that variability from the forced variability that is driven directly by the atmosphere in these studies. And so what I'm showing here is an estimate of what I call intrinsic variability on the left, which is just the variability that is not directly driven by the atmosphere, but it's coming from all the eddies and all the energy transfers across scales and all that, so that you don't get in a coarse resolution model that we were seeing before. And so you can see that you can get pretty large variability in many places where you have, to have eddy energy. And on the right here, I'm sort of plotting a ratio of the forced variability to the intrinsic variability. And so if you see red colors, that means that the intrinsic variability is not negligible compared to the forced variability. And this is for periods of 60 days. And so you see, like a lot of the tropics, you would need to account for intrinsic variability if you want to get a good sense of what the bottom pressure is doing. And this is for another band from the 2 to 12 months. Again, the same sort of plots. And on the left is the intrinsic variability of up to a few centimeters at places in bottom pressure, and the ratio of the force to the intrinsic on the right. And here you see a lot more red. So at these time scales, you can have actually places where the intrinsic variability is as large or larger than the forced variability. And so that's of course, not all of these places are very eddy rich, have a lot of eddy energy. So we have a lot of different things happening here. And so one of the things, of course, is that you have energy transfers across scales. So you can have an eddy field that's at 200 kilometers and timescales of a few weeks. But you're transferring that energy through nonlinear processes to other scales and both spatially and temporally. And so you end up with variability, intrinsic variability across a range of of scales. And you can also have what I'm trying to show here, very large intrinsic variability. So this is a pattern that we get from trying to infer trying to map intrinsic variability into EOF. And this is a very large scale pattern on the left that's intrinsic in nature, and the timescales of this pattern are shown on the right here. So you get things like monthly variability. And this is basically what you might get from having some unbalanced motion in places like a Drake passage from nonlinear processes, which then can adjust globally through wave barotropic adjustment processes and can give you some very large scale intrinsic variability. So what do we then want to do from this. So I just jotted down some thoughts here. So basically, we need to contend with the intrinsic variability that I'm showing here, and we have intrinsic variability of a few centimeters that are going to be very important to interpret some of the variability in the BPR data and the model comparisons. So the tough point about this is that this variability is essentially random, and so it's going to be very hard to address this if you're trying to match a model to the data. One way to do that is basically to try to do some data simulation. So you're constraining your model to the data, and you hope that you can get closer to the data by doing that. Of course, one problem there is that you might be, if you're constraining by using bottom pressure data, then you might be fitting signals that you don't want to fit, like geodetic signals, with the ocean model. So I think that one of the key things would be to do some kind of regional modeling where you can go lower or higher in resolution, have some data simulation method, and perhaps try to use a multiple stream of data, but excluding bottom pressure data, so that you can derive information from the other data. For example, what Randy was talking about yesterday, if you have velocity data, you can constrain the velocity, and you can obviously improve the pressures from that constraint. And then maybe you can start matching better the BPRs and removing the oceanographic signal from the BPRs. So that's where I'll leave it, and thank you for your patience.